This video is for GCSE Waves Part 1, Lesson 6, Calculating the Speed of Sound in Air. By the end of the lesson you should be able to recall a method for determining the speed of sound in air, and you should be able to take results from that experiment and be able to calculate a value for the speed of sound in air. There's quite a lot of note taking today, so by all means I'm happy for you to print off the PowerPoints as long as you read them and you complete any of the exercises that are set on. Could you now put the title, Experiment to Determine the Speed of Sound in Air? To calculate the speed of anything you need to know two things. You need to know how far that something has travelled, in our case a sound wave, and the time that it's taken to do that. To calculate the speed you then simply need to divide the distance that it's travelled, s, by the time it's taken, t. There are three methods which I'm going to talk about, two quite briefly and then one in a little bit more detail. The first method involves a person with a starting pistol and a person with a stop clock a distance s away. Now when that person fires the gun, the light from the smoke produced arrives at the person with the stopwatch almost instantly. So as soon as that person B I'm calling it here, sees the smoke, they start the stop clock. Because sound travels about 1 million times slower than light, the sound will arrive a short time later, and so the person, when they hear the sound, stops the stop clock. So that tells us how long it's taken the sound to get from the person A with a pistol to the person B with a stopwatch. If we measure that distance s, we can then use the formula up here to calculate the speed of sound. Now, there's a big problem with this method in the sense that you need large distances for this to work, because if you are talking about short distances, the sound takes a very short amount of time to reach you, and therefore it's difficult to start and stop the stop clock accurately. So we can adopt a second method which involves an echo. This has the primary advantage is that the distance doesn't have to be as large between the person making the sound and the person recording the sound. So it's exactly the same idea. Person B here starts with a stopwatch. When they hear the sound being made by the person next to them, start it, and then they wait to hear the echo back. But because the sound is having to travel there and back, you actually only need half the distance there between you and the wall. And again, we can use the simple formula speed equals distance divided by time to come up with a value for the speed of sound. The distance s in this case is in fact double the distance between the person and the wall, because the sound has got to travel to the wall and back. So whatever that distance there is needs to be doubled when we use it in our formula. Both of these methods are heavily reliant on a person's reaction time and how good it is. So in science we try and be as accurate as possible. So the next method I'm going to show you involves a piece of electronic equipment. Please pause the video and make sure that you've got the outline of what's on that slide there. Okay, can you put another title please, Experiment to Determine the Speed of Sound in Air using an Oscilloscope. Can you make a sketch of the diagram that we're going to use here? Now the sound source is going to be our old friend the signal generator, linked to a loudspeaker. We've then got two microphones which are connected to something called an oscilloscope. It's similar to those heart machines that you might see in hospital. The microphones are separated by a distance s. Now the idea behind this experiment is that when the sound is made, this microphone here, M1, picks up the sound and sends a signal to the oscilloscope. The sound then travels to microphone 2 and the same thing happens again. A little blip on the oscilloscope screen appears. So if we look at those oscilloscope traces here, we can see this is time going along the bottom. Then the microphone M1 is the first one to pick up that sound because it's closer to the loudspeaker. Okay, and then a short time later, microphone 2 records that sound. Notice it's not quite a side because it's travelled a further distance, it's further away. The important thing is that this time here represents the time taken for the sound to travel between microphone M1 and microphone M2. Now if we measure that distance S, we've got both the things that we need to calculate the speed. Distance S divided by time t will give us the speed v. Now typically these times are very small, so we're talking about milliseconds, thousandths of a second. But nevertheless, we can use this method and use it to determine the speed of sound in air. If everything is working well and we've got the correct room temperature, 20 degrees Celsius, then our answer should come to around about 346 meters per second. Again, can you take a moment to pause the video and make a copy of what's on the slide here? Okay, in your notes now, can you put a results table? Our results here. In our experiment, the distance between the microphones is 1 meter. Okay, so if you can sketch out this table here, and I'm going to talk you through the first set of results, and then I'd like you to have a go at applying that method to the other two. Okay, so this column here represents the time it's taken the sound to reach microphone 1, and in the first experiment, the first trial that we did, it took that amount of time, very small amount of time. Then the time it takes for the sound to reach microphone 2 is this one here. Now the time it takes to get from 1 to 2 is simply that time there, take away that time there. The time interval is that minus that. So if we do that, we end up with a time of 0.00294 seconds. That's how long it's taken to get from microphone 1 to microphone 2. Now I've told you here that the distance separating the microphones was 1 meter. So to calculate the speed, we used distance divided by time. 1 divided by time. So in this case, it's 1 divided by 0.00294, which gives us 340 meters per second. Remembering that the correct speed at 20 degrees Celsius is 346, that's not a bad result. Now what I'd like you to do is to work out a value for speed using the following sets of data there. So in each case, the first thing you're going to do is you're going to work out the time it takes the sound to get from 1 to 2 by subtracting that from that, putting your answer there. And then to work out the speed, it's 1 divided by that time there. Okay, so can you pause the video and have a go at completing that table? I'll go through with it shortly. Okay, so you should have found that the first row gave you a speed of 349 and the second row gave you a speed of 342, and if we calculate the mean by adding them all up divided by 3, you should get 344. Okay, this also needs to go in your notes. Analysis. Our value for the speed of sound was 344 meters per second. That was the mean. The accepted value, done by far more accurate experiments, is 346. So the difference between the two is 2 meters per second. To calculate the percentage difference, which you might be asked to do in a GCSE exam, you simply divide the distance by the true value. So that's 2 divided by 346, which gives us 0.6%, which is a pretty good result for an experiment like this.